So we're continuing on with our discussion of chapter 17, and we're looking at various methods to install alcohol functionalities and many methods to convert functional groups such as alkenes, ketones, esters, etc. into alcohols. So one of the ways that we can leverage the alkene functionality outside of hydroboration, outside of oxymercuration, and outside of acid catalyzed hydration is epoxidation. And epoxidation is very useful for the synthesis of diols and other alcohol derivatives. So the interesting feature for oxidative epoxidation is that the addition and installation of our epoxide occurs with Syn Stereochemistry. So our epoxide occupies a single face of our molecule. So in terms of our mechanism, the general mechanism for a peroxy acid, and this could be metachloroperoxybenzoic acid, or it could be, for example, trifluoro, or it could be, for example, peracetic acid, or other peroxy acid derivatives. The mechanism is the same in all cases. This is a concerted process in which our alkene attacks our electrophilic oxygen. The oxygen-oxygen bond is broken. Then a proton is removed, and our second oxygen-carbon bond is formed. This yields an epoxide and a byproduct acid. This mechanism should be familiar if you've taken 112, as this was covered as part of the alkene reaction section in 112. Any questions so far on the mechanism for this reaction? Any questions so far on the mechanism for this reaction? Okay, so one other feature that I'll just briefly discuss is that addition occurs from the least hindered face, resulting in stereoselectivity for certain products. So this is primarily covered in later organic classes, but you can get selectivity and facial selectivity in epoxidation, just like what we saw for hydroboration. Okay, so what we're now going to talk about is a method to take our epoxide and generate diol derivatives or ether derivatives of our corresponding epoxide. So acid catalyzed epoxide opening provides us access to trans diols. Epoxide opening under acidic conditions proceeds with Markovnikov selectivity and anti-stereochemistry. So we have Markovnikov Regio Selectivity and anti-stereochemistry. Further, if epoxide opening is performed using an alcohol nucleophile or other nucleophile, the nucleophile is incorporated at the most substituted position. So the nucleophile adds to the site that can most readily stabilize a carbocation. So in terms of the mechanism, the first step, we need to activate the epoxide. So under acidic conditions, we are going to protonate our epoxide. Once we have protonated our epoxide, our nucleophile is then going to attack the most substituted carbon from the opposite face. So it attacks following Markovnikov regioselectivity and anti-stereoselectivity. So we open the epoxide from the opposite face. This gives us our corresponding trans diol-like product. And then all we have to do is simply deprotonate the resulting protonated, in this case a protonated ether, and we generate our neutral product. So we have installed our nucleophile with Markovnikov regiochemistry and anti-stereochemistry. Does that make sense to everyone so far? Is everyone comfortable with this mechanism so far?
Professor, could you review what Markovnikov and anti means?
Sure. So just to review that, so in terms of Markovnikov selectivity is based on this idea that addition occurs to the most substituted carbon or the carbon that can most readily stabilize a positive charge. So in this case, as we notice, we have a secondary versus a tertiary position. Which of these positions can most readily stabilize a cationic charge?
The tertiary carbon?
Yep, exactly right. And that's why we see our addition occurs at the tertiary carbon. It's most readily able to stabilize a cationic charge. It's relatively the most electrophilic carbon in this molecule. And so our nucleophile will attack our epoxide at the tertiary carbon from the opposite phase. So when we say anti-stereochemistry, so thinking about it, if we have like a ring system here, if our two substituents, like let's suppose our two alcohols in this case, are on the same face, we call this Syn selectivity. If our two alcohols or functional groups are on the opposite faces of our molecule, we would call this anti. And this also applies to acyclic systems where we can have syn and anti products as well. Does that answer your question?
Yes, it does. Thank you.
Perfect. Any other questions on this example?
Professor, does anti only apply to like the same substituents?
Anti describes the relative location and relative stereochemistry of two substituents.
Oh, it doesn't have to be the same one, right?
It doesn't necessarily, because for example, this alcohol and this ether are anti.
Yeah. Okay. Thank you.
Perfect. Any other questions I can address on this example? And if you have a question, don't be shy to unmute and ask. Okay, so let's keep going with this and let's talk about the counterpart to epoxide opening under acidic conditions. And this entails epoxide opening under basic conditions. Now, what's interesting about epoxide opening under basic conditions is I like to think of it as a variant of an SN2 reaction. So epoxide opening under basic conditions occurs with anti-Markovnikov regiochemistry and anti-stereochemistry. So the nucleophile attacks the least hindered carbon, and the reaction does not occur efficiently for tertiary carbons. This is a textbook hallmark of an SN2 pattern of reactivity. So in this case, our nucleophile, such as our alkoxide, will attack opposite to our leaving group, which is our epoxide. The epoxide carbon-oxygen bond will break, will generate our trans or anti product. And then the alkoxide intermediate is then protonated. And we can isolate our desired diol. Notice that our alcohol is installed with anti-Markovnikov regiochemistry. Our nucleophile is installed at the least hindered carbon, and our two substituents are trans or anti to each other. And this matches our hallmark idea of an SN2 reaction in that it occurs with inversion of stereochemistry during the attack. Does this make sense? Any questions on this example? Yes, you can think of this alcohol as syn or cis with this methyl group, sure. Any other follow-up questions I can address? Okay, so let's take a look now and let's compare acidic versus basic conditions. So under basic conditions, our attack occurs at the least substituted carbon, while under acidic conditions, our attack occurs at the most substituted carbon with Markovnikov selectivity. So depending on the regio control you want, you would have to use either acidic or basic conditions. Does that make sense? Okay, so let's keep going then. And I'd like us to, for this first example, predict the products of the following reaction and draw a mechanism for the reaction. So we have the following two-step conditions. This is a typical two-step reaction sequence. And I'd like us to identify the mechanism for this reaction and predict the products for this reaction. This is a two-step process. So you may want to draw the mechanism for step 1, followed by the mechanism for step 2. So I'd like us to work on this example for about 3 to 4 minutes. And I'd like to see your responses in the chat, shared verbally, as pictures of your drawn mechanisms in the chat, or annotated on the class whiteboard using the annotate tool. And to help provoke some discussion here, what's happening in step 1 and step 2? If you can start thinking about that in terms of what's happening in each reaction step under these conditions, and what can we conclude from it? If you start thinking about it from there, then it may be a little easier to start drawing the mechanism and predicting the products. And I want the products drawn with stereochemistry. That's part of why we went over the stereochemical outcomes. And we'll take as long as we need on this example. I'd at least like to see some questions to get a sense of where we're having questions as we work through this example. I'd like to see some contributions in terms of what is happening under each of these conditions, what products are we going to see after each step. And so we know it's acid catalyzed, right? Yeah, that's the second step. So we know that the second step is occurring under acidic conditions. Yeah. What about that first step? RCO3H. What is that reagent used for? epoxide installation, right? So the first step is epoxidation. And the second case is acidic epoxide opening. Okay, so now that we have a sense of what's happening in each of these steps, would anyone like to try to predict the products or draw a mechanism for these steps? I always find that if you can think about things from a mechanistic perspective, you can notice and you can begin to understand what happens when a reaction gives a different product. In this case, these are relatively standard epoxidation, acid catalyzed epoxide opening conditions. So I'd like us to take that time now to try to draw out a mechanism and predict the products. And I'd like to see some sample products from this two-step or the product from each of these individual steps drawn out on the class whiteboard. And ideally, I'd like to see a mechanism. You can also share a photo of your work in the chat. But it's important that we're able to handle these questions. So let's keep working on this example. And I'd like to see some student responses shared in the chat, verbally, or on the class whiteboard. So, okay, perfect. A student is starting to draw out the peroxy acid, and I would recommend drawing out the structure of the peroxy acid to make it easier for this mechanism. And don't worry, there's plenty of space on the class whiteboard, so multiple students can annotate. That's why I make sure to leave 2 lines. And let me draw another substrate here, just so that way we have more space. Since I saw a third student wanted to annotate, there are 3 templates drawn. So I saw a third student wanted to draw. There's an open space available, so don't be shy to share your proposed mechanism. Because I find the physical act of drawing the mechanism helps ingrain it in your memory. And it can help reveal questions. The one thing to note, the peroxy acid has 2 oxygens. So just put another oxygen before the hydrogen. So the mechanism in blue, in terms of product prediction, the product looks reasonable, but the arrow pushing mechanism is missing a few arrows. The epoxidation is a concerted mechanism. So I'll give the students who drew in purple and blue, I'd like to see your revised arrows drawn. And I'd like to see your proposed arrow pushing mechanism. And then we'll talk about this first step. So it's great to see this range of student responses. And if we compile all of these ideas together, we have both halves of our complete picture. So we have a reasonable arrow pushing mechanism, and then we have some reasonable products drawn. And in many cases, we have the concerted mechanism. And at the end of this first step, we're going to get our tri-substituted epoxide. Okay, so to give us a bit of a landmark before we continue, what I'm going to do is I'm going to draw out that first step, the epoxidation step. And from there, we can build on it. So for this first step, for epoxidation, we have our peroxy acid. Okay, so the main thing to note for this epoxidation is it's a concerted mechanism. So first, we have attack, we break our oxygen-oxygen bond, we pull off our proton, let me draw it like this, and then we form a carbon-oxygen bond. So at the end of this concerted mechanism, we get out an epoxide as a mixture of enantiomers. I'm going to draw the epoxide on the top face just for convenience. So we end up with the following product plus the enantiomer. And the student responses reflected that for this first step. Now, as students are already starting to draw the second step, I'd like us to take this epoxide intermediate, and if we subject it to the second step reaction conditions, if we treat it with aqueous acid, what products will we get, and what will their stereochemistry and regiochemistry look like? So we're dealing with acid catalyzed epoxide opening. So what kind of stereochemistry and regiochemistry will we observe? So let's break out the annotate tool once again, and let's try to share our responses in the chat or verbally. What do we think will happen if we take our epoxide from step 1 and we treat it with acid catalyzed epoxide opening conditions? And I would welcome you to comment in the chat what kind of regiochemistry we would see and what kind of stereochemistry we would see. Are we dealing with Markovnikov or Anti-Markovnikov regioselectivity? And are we dealing with Syn or Anti-Stereoselectivity? So let's take another 3 to 4 minutes to build on this example. So a student has drawn the epoxide. We have one student commenting, or multiple students commenting, that we would expect Markovnikov regio control and anti-stereoselectivity. That is correct. So let's try to visualize that with a mechanism. So we're dealing with acidic conditions, and we have this epoxide. So before we have any attacks, how do we activate the epoxide? How do we prime the epoxide for reaction? Protonation, exactly right. So we protonate our epoxide. And now, following our class discussion under acid catalyzed conditions, we have an intermediate that reminds me a lot of like a mercurinium intermediate. And we're going to open this protonated epoxide following Markovnikov regio control. So where is our water? Where is our nucleophile going to attack? So we have 2 carbons. So I'll label them here, A and B. Which carbon is our nucleophile water going to go for? Where are we going to attack? A, yep, carbon A, 100%. Yep. So we attack with Markovnikov regio control, and then we open up our epoxide. One more arrow to open the epoxide. So we attack and we break the carbon-oxygen bond on the same carbon that's attacked. Yep, exactly right. Perfect. And that gives us our diol product. And we notice, let's draw out our product. And what does the class think? Syn or anti-product? Are we going to get the syn or anti-product in this case? I see some students typing anti. What does the rest of the class think? And don't worry, the student annotating can keep drawing as well. We see an overwhelming response that the anti-product is generated. So when the water attacks and opens our epoxide, it attacks from the opposite face. So our alcohol is on the bottom face and our other alcohol is on the top face. Yep. So the product prediction looks good and the mechanism looks reasonable. Let me clear this and then we'll provide the instructor solution. And one thing I'd like you to note that I find I really encourage you to try on a separate sheet of paper or whenever possible, draw out the mechanisms, because what you're going to find is in later chapters, you're going to start to have to consider what happens when a reaction gives a new product that you may not necessarily have seen before, but you can understand the mechanism by breaking it down into fundamental steps. Yeah, I certainly can. I appreciate it when students draw, even if they're drawing with a mouse, because I find it really helps ingrain in the muscle memory of drawing a mechanism. So the first step, we're going to protonate our epoxide. So that generates our active intermediate. From there, our nucleophile, in this case water, is going to attack with Markovnikov regio control and anti-stereoselectivity. That is going to give us the following trans diol. Now, it's really important when you're dealing with acyclic systems, do not modify your main chain. If you start rotating your main chain, you're going to have to be careful that your stereochemistry is properly represented. That's why I draw the main chain consistently the same throughout. It just saves me the headache. Now, one thing I do want to note is, as the last step, you do have to deprotonate your, in this case, your alcohol. In that case, we get as our final product the following trans diol. So this is a wonderful method to make trans diols from alkenes. Now, one thing I want you to ask, is it okay for me to put the plus enantiomer? Do we have genuine enantiomers in this case? So let me draw out the other product that we would get. So here's the other product that we would get. So my question to all of you is, are these genuine enantiomers?
No.
Could you elaborate?
I think if you rotate them, they would be identical, right?
How so? Which bond would you have? So one check to verify. So let's draw out our hydrogen. So one check to verify and to look for the presence of enantiomers is to assign stereochemistry. So in this case, this center is S. In this case, this center is R. In this case, the center is R. In this case, the center is S. So as you notice, if the configuration is the opposite at each of your stereocenters, then these two molecules would be genuine enantiomers. Does that argument make sense?
Yes.
Perfect. And that's always a good way to check. Most cases, putting plus enantiomer is okay. You always just want to do an internal check for symmetry, because in some cases you may have molecules where after generation of your diol, you end up with a symmetrical molecule. Does that point make sense? Any questions on this example? Okay, so now we're going to do another example. And this time we're looking at another alkene geometry. And I'm going to show the first step. We should all know what's happening in the first step, right? What's happening in the first step? Just like before, we're treating this alkene with a peroxy acid. So what's happening in our first step? Epoxidation, yep. Though normally MCPBA is used, but peracetic acid is often used for simplicity in terms of drawing the mechanism, and it's easier for students to draw the mechanism for. Though practically you probably wouldn't want to use peracetic acid because it's not a very fun reagent to handle. Anyway, so we have our same concerted mechanism, and that generates our epoxide. I'm going to draw it on the top face. It's perfectly arbitrary. And you also get the enantiomer. In this case, we are justified in writing plus enantiomer because we do have two different substituents. This epoxide is asymmetrical. Now comes the interesting part. We treat this mixture with sodium hydroxide and water. So, what is happening in the second step? What is our Regio selectivity and what is our stereoselectivity for this second step? So we see a lot of students commenting that we have anti-stereo control. And in terms of regio control, it's also anti-Markovnikov. What do we call the reaction conditions for the second step? What type of reaction is this second reaction? Basic epoxide opening, and I like to call it just an SN2. So we're dealing with basic epoxide opening. So then, would anyone like to volunteer a mechanism and structure for our product? We have plenty of space available, so I'd like some students to try drawing out the mechanism for this basic epoxide opening. And just to make things a little bit easier, I'm going to draw out this methyl, and we'll put this methyl group in. And that way, it'll make it a little bit less difficult to draw out the product. just to note, if you had a choice between methyl and ethyl, you would get a mixture that would slightly favor addition at the methyl because it's less hindered. But I'll just put in this methyl group to make it a little more clear cut. So we have a student drawing out our structure. And we just added this methyl to the adjacent carbon to make it a little less ambiguous. Okay, now we have a nucleophile, which is hydroxide. And our nucleophile, in typical SN2 fashion, is going to attack the least hindered carbon. So we have two choices, A and B, and we immediately attack the least hindered carbon, exactly. Anti-Markovnikov regio control. And just like any SN2, when we attack our carbon with a leaving group, what bond breaks? So there's one other arrow we have to draw. Perfect, exactly right. We break the carbon-oxygen bond, and that in turn gives us a trans diol. But as we notice, the Regio selectivity is different. So let's draw out our trans diol product. And remember, when you're dealing with an acyclic system, it's really important that you keep, as drawn, the main chain is kept consistent. That's good. Our alcohol installed via our nucleophilic attack is installed on the bottom face, exactly right. And what about the other alcohol? Is it on the top or bottom face if we have an anti-product? Perfect, exactly right. So we have the shown product and the enantiomer. So allow me to clear the student response and let's go over this example together. But the drawn mechanism was exactly correct, and I greatly appreciate students sharing their responses using the annotate tool and students typing in the chat to help guide our discussion. Okay, so hydroxide is going to attack at the least hindered carbon, and it's going to open our epoxide. That in turn generates the following alkoxide intermediate, and our newly added alcohol is installed on the bottom face. For our last step, since we have to isolate neutral intermediates, we're going to protonate our alkoxide intermediate with water. So that in turn gives us the following product plus the enantiomer. So I'd like you just to take a moment. To compare. So let's zoom out a little bit. Okay, so when we look at our two products, from these two different conditions, does everyone notice how we get different products depending on our reaction conditions? Does everyone see how the conditions control the Regio selectivity and as a result our product outcomes? Any questions on these two examples? If not, let's continue on then. So another method that complements acid and base catalyzed epoxide opening is Syn dihydroxylation. So all of these mechanisms up to this point have been covered previously in Organic Chemistry 1, and we're now starting to fit each of these different reaction processes in the context of synthesis. And we're thinking what reactions yield what product regioselectivity and stereoselectivities. So if we want to install a diol with Syn selectivity, the best method or the most common method used is osmium tetroxide or another sharpless variant for this dihydroxylation. So osmium tetroxide followed by sodium bisulfite allows us to convert an alkene into a diol. So what's important to note is in the first step, when you treat your alkene with osmium tetroxide, the intermediate formed is actually an osmate ester. Then in the second step, sodium hydrogen sulfate and water promotes hydrolysis of this osmium oxygen bond, and this sodium hydrogen sulfite serves as a reducing agent to cleave off and break up this osmate ester. Now, you can just as easily use potassium permanganate, but you have to be really careful and make sure it's run under cold, dilute conditions. Otherwise, the diol is cleaved. Many of these diols can be selectively cleaved with sodium periodate or cleaved in the presence of permanganate to generate diketones. So osmium tetroxide followed by sodium hydrogen sulfite is the most common sequential series to generate a cis diol. Does everyone see how the two alcohols are cis to each other? Any questions on this example? Okay, so let's keep going then. And let's try to predict the products of the following reaction. And I'd like you to draw a mechanism for just the first step of this reaction. So we have a trans alkene, and we're treating it with osmium tetroxide and an oxidizing agent such as NMO, which just helps turn over the osmium. And then in our second step, we're treating it with sodium hydrogen sulfite and water. Would anyone like to volunteer and draw a mechanism for the first step for this reaction? And would anyone like to predict the products from this reaction? Yep. So we have attack of our osmate ester. The osmium tetroxide is installed and attacks in such a way that both of our alcohols are installed on the same face. And would you be able to draw that product from this first step? So what would that intermediate osmate ester look like? Yep, so our osmate ester is formed and installs our diol functionality on the same face. Yep, so let's draw the first step. So let's clear that student annotation as the student drawn mechanism looks exactly reasonable. So we have our osmium tetroxide. It attacks on the same face. That in turn generates our osmate ester. And then from there, we can sequentially cleave off the osmate ester. And that gives the following diol.
Do we need to know the mechanism for that?
As it involves a metal-based intermediate, I can show it to you, but it's a little bit steppy. Generally, I will tell you explicitly whether I want just one step or both steps of the mechanism. So just for any generic sort of osmate ester. So in the first step to this case, what we're going to do, let's see. So currently these are under slightly basic conditions. So you can have like an equivalent of hydroxide attack your osmate ester. And then from there, your intermediate collapses and you kick out your Okay, so essentially what happens is you're hydrolyzing off your osmate ester sequentially. So you can attack with a nucleophilic species like hydroxide, and then rather than kicking out hydroxide, you kick out one of the oxygen atoms bonded to your osmium. And so you can repeat this process. Not particularly difficult. It's just a somewhat steppy mechanism to draw out. Okay, so that's the complete mechanism. So we get to the alkoxide, we've cleaved off our osmate ester, and then from there, your oxidizing agent will oxidize your osmium back up so that way it can continue on the catalytic cycle. The NMO essentially reoxidizes this osmium intermediate back up to osmium tetroxide. Does that answer your question? It's very similar to the mechanism, for example, for like transesterification or ester hydrolysis. In this case, you're just hydrolyzing rather than a carbon ester, you're hydrolyzing an osmate ester. Does that make sense?
Yes, thank you.
Perfect. Okay. Yeah, the second alkoxide will just pull off a proton from water. Yep, exactly right. So the one thing I want to highlight is you have to pay attention to your alkene geometry. Because for example, if we start with a cis alkene, so I'll just show the mechanism here for the first step since we've done this before as a class. So we generate the following osmate ester. And then from there, it's cleaved off to yield the following diol. Now, in this case, is it appropriate for me to put plus an enantiomer? Is it appropriate in this case?
No.
That is correct. And why is that? Looking at this product, what's special about this product?
It has symmetry.
Yep. And what do we call that?
Meso.
Meso, yep. So it's a meso product. So it's always important to pay attention to your structure and the stereochemical outcome of your reaction. Does that idea make sense? Perfect, perfect. Any questions on cis dihydroxylation using osmium tetroxide? Okay, so one thing that I'd like you to note is from an alkene, you can get cis 1,2 diols using osmium tetroxide, and you install your diol with Syn Stereochemistry. Trans 1,2 diols can be obtained via acid catalyzed hydrolysis of epoxides, which generates your diol with Anti-Stereochemistry. So these are two complementary methods to give two different stereochemical outcomes. Would anyone like to comment as well? Would anyone like to comment as well on one other very important point that we need to make with regards to epoxide opening? Do I just have to use water as my nucleophile for epoxide opening? Or do I have a little more freedom? What do we know about epoxide opening? So what was the central point that I made in epoxide opening? Like for example, let's look at an example here. If I wanted to take this structure and I wanted to advance it all the way to something that looks like this. So you can also use basic conditions for epoxide opening, that's true. Can I make a structure like this from my epoxide? If I get an epoxide, can I open the epoxide with essentially any nucleophile I want. For epoxidation, does it have to be, well, it can be an alcohol, but it really can be anything, right? Since this is an SN2 reaction. So epoxide opening tolerates a range of nucleophiles. So you can essentially use almost any nucleophile you want for epoxide opening under basic or for acidic conditions, you generally have to use an alcohol-derived nucleophile. But under basic conditions, really you can open that epoxide with almost any nucleophile that you want. And that's one of the strengths of epoxide opening. It doesn't just get you to trans diols, it gets you to trans addition products where you've added a nucleophile trans to an alcohol. Does that point make sense to everyone? That epoxide opening tolerates a wide range of nucleophiles? So, dihydroxylation and epoxide opening are two complementary techniques with two different stereochemical outcomes. You can also, within epoxide opening, control the regiochemistry and modify what nucleophiles are tolerated under the reaction conditions. So it really gives you an access to a range of structures. Does that answer your question? Yep, yeah, but that can be easily done during the quench step. To answer the question in the chat, you would need a proton source to quench the alkoxide in the end, but that can be done during the quench or cleanup step of the reaction. Okay, so we've covered methods to install diols. So what we're now going to do is we're going to start to think about these reactions in terms of synthesis. So I'd like us now to consider the reactant and product, and I'd like us to think what conditions and reagents would we use that we may need multiple steps here to obtain the following product from the given starting material. So suppose you wanted to make this diol. What conditions would you use? So let's think about this first one for a moment. So let's list some features. So we have a diol, and what is the stereochemistry? Trans, yep. So then, what methods do we have at our disposal to make a trans diol? What method do we have at our disposal to make a trans diol? Acid catalyzed epoxidation and epoxide opening, or we can use base catalyzed epoxidation and epoxide opening. Both methods would work. So in this case, we put as condition 1, what are the conditions to generate the epoxide? What reagent should we use? A peroxy acid. So we can use, for example, peracetic acid. Okay. And what conditions would we use for the second epoxide opening? So you can choose either acid or base catalyzed. We don't have to worry about regio control in this case. What would you use for the second step? H3O plus or NaOH. Let's use base catalyzed conditions. So we have NaOH, and we can have water as a co-solvent in this case. Yep, so that would give us this trans product. So just to show the mechanism for that, because it's important to be able to rationalize your predicted product using a mechanism. So from our first step, we'll get the following epoxide. And then from there, hydroxide will attack our epoxide and open up the epoxide, giving us the following trans diol. Yep, perfectly reasonable set of conditions. Does this first example make sense? Any questions? Okay, let's look at this next example. And we have the following reactant, and we want to generate the following product. So what conditions would we have to use? To answer the question in the chat going up here, if you used an acid like hydrochloric acid, you wouldn't see much of the chlorinated product, because if you got any of the chlorinated product, or if, well, first, chlorine is not a better nucleophile than water. And second, if you did get any chlorinated product, it would immediately ionize and you get cyclization back to the epoxide. So generally the nucleophile that you install has to be a pretty decent nucleophile and a pretty poor leaving group. Does that answer your question? Okay, so let's look at this next example, and I'd like us to try and think, what conditions can we use to get this desired product from this indicated reactant? And let's pay attention to our product. What's so special about our product? Our product is a cis diol. So what conditions would we need? I have one student mentioning in the chat, osmium comes to mind for cis dihydroxylation. Does anyone have another suggestion? Let's try to get a few responses in the chat. What conditions should we use? I see students mentioning osmium. So what two-step sequence do we need then? What two-step sequence of reagents? So in this case, we would add osmium tetroxide first with either pyridine and NMO just to turn it over. You typically don't use stoichiometric osmium if you can help it. And then for the second step, you add sodium hydrogen sulfite and water. Yeah. So mechanistically, this would give us a cis diol plus the enantiomer, of course, in this case. Just to walk us through the mechanism for that. It's always important that you're able to draw mechanisms to rationalize why you observe the products that you observe. One hint that you may need to revise your reaction scheme is if you can't figure out the mechanism that gets you from the reactants to products using your given reaction conditions, that's usually a sign that something needs to be revised or reconsidered. Okay, so as we see, osmium tetroxide followed by reductive cleavage would give us the desired cis diol. Any other questions on this example? Okay, let's keep going then. And let's consider the next scheme. What conditions and reagents would we use to obtain the following product? So in this case, we have an alcohol installed relative to our alkene, and let's try to diagnose what's going on here. So what is our regioselectivity? What is our regioselectivity? And what is our stereoselectivity? Let me write this out. What is the regio and stereoselectivity in this case? That's our first step to figuring out the reaction conditions. So our regioselectivity is Anti-Markovnikov. Okay, what about our stereoselectivity? So with respect to the hydrogen and hydroxyl group, they're installed in a Syn manner. So what conditions spring to mind then? What conditions give anti-Markovnikov installation of our alcohol? However, the hydrogen and the alcohol are installed Syn. One thing to note is that this stereocenter is well defined. So oxymercuration typically gives Markovnikov selectivity, and the stereocenter where the hydrogen is installed is typically installed as a racemate. What other condition? What is the textbook condition for anti-Markovnikov installation of an alcohol from an alkene? There's actually only one set of conditions that we covered that would accomplish this transformation. Hydroboration, exactly right. So what two-step sequence would we need for hydroboration? So we have BH3 and THF. Yeah, that's the first step. That makes our alkyl boron intermediate. You can also use B2H6. Any borane will do the trick. And then you can do H2O2 and NaOH. Just in case you're curious, this hydroboration can, the boron reagent can be modified to change the facial selectivity, potentially introduce an enantioselectivity or introduce other stereoselectivity. In this case, we get our product along with its enantiomer. In most cases, we're making a mixture of enantiomers, unless we start with the defined enantiomer. Does this example make sense? Any questions on this example? Okay, so let's look at this next case. In this second example, let's think about the regiochemistry or regioselectivity. And let's try to identify the stereoselectivity. So what do we see in this next case? So in terms of selectivity, we see for regioselectivity, we have Markovnikov regioselectivity. And in terms of stereoselectivity, just not available. The reason for that, if we look at this molecule, what's special about this molecule? It's symmetrical. Yep, it's a meso compound as well. So like even if this there's no well, it's not even meso, it's just more correctly it would be called achiral. There's no stereocenter found in this molecule. It's perfectly symmetrical. And this that correction that I made is really important. There's a fundamental difference between meso and achiral. Meso compounds have chiral centers but are symmetrical. Achiral compounds are symmetrical and do not have chiral centers. So there's no stereocenter to be had in this molecule. Does that explanation make sense to everyone? It's a critical distinction.
Could you repeat that one more time?
So meso compounds are they are symmetrical. They're meso compounds. They have centers with 4 or more different substituents. They have centers that can be chiral centers, but because they're symmetrical, the two or the enantiomers are equivalent. When we talk about achiral compounds, none of these centers are actual stereocenters. The molecule is perfectly symmetrical and each stereocenter has 2 equivalent substituents. So there is no stereocenter found in this molecule. Well, in a meso compound, there's a center that can be a stereocenter, but the molecule itself is not chiral. Even if you isolated a single quote unquote enantiomer, it would not rotate plane polarized light. Does that idea make sense?
Yeah, that makes sense. Thanks.
Mm-hmm. So this one, no matter how hard you try, there's no stereocenter present. And that's why I didn't draw the dash or wedge in that case. Okay, so we have Markovnikov installation of an alcohol, and a hydrogen is just installed wherever. What conditions could we use? Markovnikov installation. That's a very important and pretty interesting point. We have one set of conditions, oxymercuration, so mercury acetate and water followed by sodium borohydride. Or what other conditions could be used? What other conditions gives Markovnikov installation of an alcohol? Suppose you really didn't want to use mercury if you could get away with it. What other conditions would you use?
Could we use hydroboration?
Hydroboration gives anti-Markovnikov.
Oh, right. Thank you.
But another variant would be acid catalyzed conditions. So we can just treat it with H3O plus and water. because acid catalyzed hydration also favors Markovnikov selectivity. And in this case, we don't necessarily care if it's a racemate. Does that idea make sense? And practically, if we were gonna run this reaction in a teaching lab, we would probably use the acid catalyzed conditions because mercury is not practically very fun to handle because it's relatively toxic. Does this next example make sense? So there are two possible correct answers. So a racemate it generates a mixture of stereoisomers. So it doesn't install the alcohol and hydrogen with any stereo control. Under acidic conditions, it's just installing the alcohol from either face of our carbocation intermediate. Because under acidic conditions, we're going through a carbocation intermediate. It can be attacked from either face. And as a result, you get a mixture of stereoisomers that's functionally racemic, or a mixture of stereoisomers. Does that answer your question?
Yeah, it does.
Perfect, perfect. Now let's look at this second example. This one looks similar to this previous example, but it has an odd quirk due to the substrate's structure. So in this next case, we want to install this alcohol. What is the Regio selectivity? Looking at this alkene here. Starting from this alkene. Wait, from this alkene. So position 1 and position 2. What position is most substituted? 1 or 2? 2, right? So the Regio selectivity for this reaction would be Markovnikov, right? Because with respect to this alkene, our alcohol is installed at the most substituted carbon, right? Markovnikov selectivity is not the most substituted carbon, period. It's the most substituted carbon for the alkene or epoxide that reacts. And stereoselectivity, again, is sort of not available. In this case, this is a genuine stereocenter. So we will get a mixture of enantiomers. Now, can we avoid using mercury in this case? If I really wanted to avoid using mercury, could I make this transformation occur under acidic conditions? Would acidic conditions work to accomplish? I see one student typing no. Would you like to elaborate on that? So let's suppose I just treated this under acidic conditions. Acidic conditions facilitate rearrangements. That is correct. Acid catalyzed alkene hydration goes through a carbocation intermediate, and it in turn has all of the baggage associated with a carbocation intermediate. And what you will see, in fact, is that you will see hydride shifts. So at the end of this reaction sequence, rather than isolating the desired alcohol, what you would instead isolate is this tertiary alcohol product. So acid catalyzed conditions would not work. So what conditions have we talked about and have we discussed previously that install an alcohol with Markovnikov selectivity without rearrangements? What conditions would we use for this particular substrate? What conditions should we use then? What conditions get around these rearrangements? Oxymercuration, exactly right. So we are forced in this case to use mercury for oxymercuration conditions because oxymercuration sidesteps a carbocation intermediate, and as a result, we don't see rearrangements. Does this example make sense? And does this point that I'm trying to make sense? Any questions about the topics covered today during this lecture? So if not, this is a good stopping point for today.